Okay, so we're going to start up on sequences here. So important for a sequence is here's some examples of it. It's just when we have a set of numbers just going in an order, not adding them or anything. They're just saying, like, for instance, this is 1/2, then it's 2/3, and 3/4. And then we can typically write it out in some form of explicit notation here. So we're using the end values right here. Let me see if this will pick it up better. Okay, so that's what a sequence is. So what's important for a sequence is we want to find out if that sequence eventually is going to converge or diverge. Okay, so it converges if we can find the limit of that sequence and it actually gives us a number. Otherwise, it's going to diverge. All right, so nth term of an arithmetic sequence, you should have learned this back in pre-AP pre-calculus or just regular pre-calculus or whatever they're calling it these days. But this is going to be a sub n is equal to a sub 0 plus d n minus 1. I've also seen it called this a sub n equals, actually this should be a sub 1. I don't know why my notes have a sub 0. So that should be a sub 1. So whatever the first term is. And then this would, another way I've seen it is the initial term plus d times n. So those are two different ways I've seen it written for an arithmetic sequence. So the first term plus the difference times n minus 1, or this one is the initial term, so not the first term, but like the term that would be before that, times plus the difference times n. For geometric, this one I don't play around with too much. It's just going to be the first term, and then it's going to be r to the n minus 1. R is going to stand for the ratio. So if we can pick up that one of our sequences is one of these, it kind of makes this a little bit easier to figure out if it's going to converge or diverge. Because if it's arithmetic, it's going to diverge because arithmetic keeps increasing or keeps decreasing. Whereas geometric, yeah, it could keep increasing or decreasing, but if the r value is smaller than 1, or the magnitude of it rather, so it could be negative. If it's smaller than 1, then it will converge. Okay. So let's go ahead and determine whether the sequence converges or diverges, and if it converges, find the limit. If it diverges, show why. So essentially, we just need to show the limit here. So here's my sequence here, and this is actually giving me the definition, which is totally awesome. So this one is a geometric, and so this one will converge, and we'll show why here in a second. So this is going to converge. It is a geometric. And not only that, but the ratio is less than 1. If this was a 2 to the n minus 1, then it's going to diverge. So the limit as n approaches infinity, because n is my variable, 1 over 2 to the n minus 1. Well, we can rewrite that, by the way, as the limit as n approaches infinity as, well, we can separate this as 1/2 to the n all over 1/2 to the 1, because by definition, if I'm going backwards here, if it's the same base, it would just be the base n minus 1. All right, that's just a exponent rule. So this is really equal to 2 to the limit as n approaches infinity of 1/2 to the n. And then so this is an exponential that is getting smaller and smaller and smaller, so that this is eventually going to reach 0. So this first example converges, and it converges all the way to infinity, closer and closer to 0. The next one is almost exactly the same here, except you're going to, since you have a negative, you have to deal with whenever n is odd or when n is even. Okay, and it's super similar to this one. So really what this is going to turn out to be is that we're going to get negative 1 to the n minus 1 times 1/2 to the n minus 1. Because what I'm doing is I'm taking out that negative 1 of that part. So that's all I'm doing, is I'm just taking out this negative 1. Okay, so this is going to turn into, just like I did over here, I'll kind of skip a couple of steps here because I don't need to show everything. This is going to turn into negative 1 times n to the 1 times 2 1/2 to the n. So this is going to turn into this. Okay, so what's going to end up happening here is we're going to get different values if this is odd or even. So if n is odd, I'm going to end up with 2 1/2 to the n. Okay, because everything will be positive, and I just showed this work over here, so this would converge. All right, if n is even, then I will have that negative, so I'll get negative 2 1/2 to the n. In which case, you'll just have the same thing over here, but you'll get negative 2 times 0, which is still going to be 0. So this converges to 0 for both cases. All right, so I didn't formally go through everything because this is the same exact problem over here. Just if it's even, it's slightly different, but all the work's right there. I don't want to really have to go through that. For this next sequence, this one is going to diverge. I know that because I take the limit as n approaches infinity of sine of n. Sine, if you remember, keeps changing. It oscillates. So it's going to diverge. I'll write down y right here. Okay. Going to this one right here. This is a geometric one, okay, where r is less than 1, so this is going to converge. I'll show you the work. 3/5 to the n. So we just need to show this formally. This is the same thing, by the way, as the limit as n approaches infinity of 3 to the n over 5 to the n. In both cases, anyhow, it's going to go to 0 because it's going to grow faster on the bottom than it does on the top. So this is going to be 0, so this is going to converge. This one, if I were to write this one out, you get the limit as n approaches infinity. So it's the same thing, but I'm just going to flip-flop these as 5 to the n over 3 to the n. This is going to go out to infinity because the top grows much faster than the bottom. So this is going to diverge. And then this one right over here, I don't know. Let's go ahead and find the limit. So let's do the limit as n approaches infinity. Well, I do know, but we'll just pretend I don't. So we're going out to infinity here. So if you look, these have the same powers. So this is actually going to end up giving me a 3/5. So in this way, this will converge. So we're using that unit 1 stuff here to show that this converges. So I already talked about this, but this is just going into your notes. That for a geometric series, if the absolute value is less than 1, it's going to converge. If it's greater than 1, it's going to diverge. So that's this scenario, and that's this scenario, pretty much. Okay. So for this one right here, this one's kind of a weird one. So just take the limit as n approaches infinity of 3 plus -1 to the n. So if we were to actually write this out, maybe it's just easier just to write out this sequence. If n is 1, I'm going to get 2. If n is 2, that would make that positive. That's going to be 4, then 2, then 4, then 2, then 4. Then you get the idea. It's going to keep alternating. So this limit does not exist. It oscillates, so it diverges. Okay. This one right here is going to be a little bit trickier. Sorry, infinity. So ln of n all over n. So n actually grows faster than ln of n. So this is actually going to equal 0. So this converges. And if you don't believe that, you can actually L-hop it, because if you plug in an infinity, you'll get infinity over infinity. So you can always L-hop that one as well if you don't believe me that one is 0. And then this one, with the factorial stuff, just to remind you what factorial is, like n factorial is going to be n times n minus 1 times n minus 2, and so on and so forth. Okay, so you just keep multiplying and you keep taking away a number until you get down to 1. So the easiest thing to do here is to kind of rewrite this. So this is n plus 1 times what's lower than n plus 1 is n times n minus 1 times, and then just get that pattern going. And then this is going to be n plus 3 times n plus 2 times n plus 1 times, put a little time sign between there, times n, and you get the idea right there. So what's going to end up happening here is the n plus 1s are going to end up canceling out. The n's are going to cancel out. And then everything afterwards is going to cancel out because it's the same pattern. So this is actually going to equal 1 over n plus 3, n plus 2. So now we take the limit of this. So the limit is n approaches infinity, 1 over n plus 3, n plus 2, which the bottom grows faster than the top. So we're going to hit 0 here. So we are going to converge, and that's going to wrap everything up that we have here on sequences.